Hi, my name is Kai Han. I'm a professor at University of Science and Technology of China. This talk is about efficient and effective algorithms for revenue maximization in social advertising. This is a joint work by Kai Han, Enwei Wu, Jingtang, Shangcui, Xingdam Asley, and Lux V.S. Lakshmana. In this talk, we'll first introduce the motivation of our work and the definitions of the revenue maximization problem. After that, we'll discuss the limitations of previous studies and then introduce our algorithm design in detail. Finally, we'll discuss about the performance evaluation before concluding our work. With the proliferation of online social networks such as Facebook, Twitter, and WeChat, as well as the availability of rich information in OSNs, there emerge great opportunities for social advertising, where social network platform owners and advertisers can gain revenue through information propagation in OSNs. Here is a typical social advertising paradigm. The social network platform shows promoted posts in the newsfeed of OSN users, and these promoted posts can take various forms, such as images, videos, and hyperlinks to advertisements. After a user sees a promoted post, she may react to it by performing a social action in the form of comment, like, or reshare, which is counted as an engagement with the advertisement. And then the advertiser should pay a unit amount to the OSN platform owner for the engagement. The promoted posts can propagate in the network as a result of the user's social actions, leading to more engagements of the ad. Actually, the described social advertising paradigm has already been implemented or experimented with in several major companies, such as YouTube, Twitch, Instagram, and Facebook. For example, YouTube and Twitch currently pay content creators, that is, influencers selected as seeds, a portion of the revenue from a video ad included in the content. IGTV ads appear when a user clicks to watch an IGTV video in their feed, and the ads can propagate virally in the Instagram network. Similar applications also appear in Facebook stories. Actually, the considered social advertising paradigm has already been justified by researchers in the area of advertising based on real cases in marketing. In the social advertising paradigm, we call the OSN platform owner as a host, who selects initial seed users for each ad and get paid for the total ad engagements. There are multiple advertisers. Each of them has a budget BI to pay the host for the engagements and also the seed users for incentivizing them. The goal is to select some influential seed users to maximize the expected revenue of the host under the budget constraints. Now we introduce the formal definition of the revenue maximization problem studied by this paper. For the influence cascade model, we use the well-known topic-aware independent cascade model, which extends the independent cascade model. Roughly speaking, under the TIS model, the probability for a node U to activate its neighboring node V depend on both the topic distribution and the topic-aware influence probabilities. More detailed description of the TIS model can be found in the celebrated ICDM 2012 paper. Given a social network budget constraints, CPE value, and seed costs, the revenue maximization problem aims to find a seed allocation, that is vector S, that maximizes the total revenue of the host under the budget constraints, where we use SI to denote the set of seed nodes selected for advertiser I, and use pi I SI to denote the revenue for selecting SI. Pi I SI is defined as the production of CPEI and sigma I SI, where CPEI is the cost per engagement of ad I. It is known that the RM problem is essentially a problem of submodular function maximization with a partition matroid and multiple submodular knapsack constraints, which is NP hard. Moreover, Even computing the influence spread of any given node set is known to be NP hard. To our knowledge, only Astley et al. In VRDB 2017 have studied the RM problem under the assumption that there is an oracle to compute any seed set's influence spread. They proposed two greedy algorithms called CA greedy and CS greedy, which iteratively selects an element to maximize the marginal gain or marginal rate. The approximation ratios of these two algorithms are quite complex and are listed here. In practice, there is no oracle to compute the influence spread of any seed set. So Astley et al. Further proposed two algorithms dubbed TICARM and TICSRM, which revised the original CA greedy and CS greedy algorithms based on the sampling methods proposed in Box et al. 2014 and Tang et al. 2014, achieving worse approximation ratios depending on the parameter epsilon. However, the algorithms of Astley et al. Suffer from two major deficiencies. First, the approximation ratios of CS greedy and CA greedy can be arbitrarily small, as they depend on the input social network instance. Second, the computational overheads of their algorithms can be very large on the TIC model, and their running time and memory consumption both grow drastically when epsilon gets small. In this paper, we propose new algorithms to address the limitations of prior studies. For the case that there is only one advertiser, we present a simple greedy algorithms that iteratively selects an element whose marginal rate is maximized. We prove that these greedy algorithms can achieve an approximation ratio of 1/3 under the single advertiser case. However, such a nice approximation ratio does not hold for the case of multiple advertisers, as the marginal rate of the current selected element, that is UI, in the greedy algorithms could be smaller than an unselected element, VJ, in the optimal solution under the case of multiple advertisers. Now we introduce the overall idea of our algorithms for the case of multiple advertisers. An intuition is that we want to select elements whose marginal gains and marginal rates are both good, but it is hard to simultaneously achieve these two different goals. So we provide a framework to strike a balance. In this framework, we first call an algorithm threshold greedy to greedily select elements with large marginal gains, but only accept them if their marginal rates are better than an input parameter gamma. It can be seen that the threshold gamma can affect the numbers of selected elements with large marginal gains or marginal rates. To optimize the performance of threshold greedy, we further use the search algorithms to find a suitable gamma. More details of the threshold greedy algorithms are described as follows. First, we initialize three candidate sets SI, DI, AI to the empty set for each advertiser I, where DI is a singleton set containing the first selected node causing budget overflow. Next, we use the greedy plus greedy threshold strategy described before to select the nodes in SI and DI for each advertiser I, and then use the greedy algorithms to find AI if only the budget of advertiser I is depleted. Finally, we choose the best candidate set from SI, DI, AI for each advertiser I, and call the fill procedure to select more nodes for the advertisers whose budgets are not depleted. The fill procedure adopts a greedy strategy that iteratively selects elements to maximize the marginal rate. The search algorithm finds an appropriate threshold gamma based on binary search, where an input parameter bmin is used to guide the searching direction. For example, if threshold greedy returns b smaller than bmin, then it implies that gamma could be too large, and hence few advertisers deplete their budgets. So the search algorithm would try a smaller gamma. Another input parameter tau is a parameter reflecting the trade-off between accuracy and efficiency. For example, if tau gets smaller, then more iterations would occur in binary search, which results in better accuracy. Here we provide a sketch of our RM with Oracle algorithm, which consists of the procedures described before, and can solve the RM problem under the assumption that there is an oracle to evaluate the inference spread of any given node set. The RM with Oracle algorithm can achieve an approximation ratio lambda described here. It can be seen that lambda only depends on the number of advertisers and does not depend on the input network instance, so it can be regarded as a constant given the number of advertisers. In practice, computing the inference spread is an NP-hard problem, or it is a Shapir-hard problem. So we provide a novel uniform sampling method to make our algorithm more practical, which is based on the concept of a reverse reachable set. The uniform sampling method first samples an advertiser I with probability proportional to CPEI, and then generate an RR set for advertiser I. Using this uniform sampling method, we further provide a one-batch sampling algorithm whose main idea is to generate a sufficient number of RR sets to guarantee the approximation ratio and also make the budget overshoot caused by sampling error small. As the one-batch sampling algorithm could generate a large number of RR sets in one batch, it may have large computational overheads. In order to improve the time efficiency, we further propose a progressive sampling algorithm dubbed RMA. Roughly speaking, the RMA algorithm adopts a trial and error strategy to generate just enough R sets to improve the time efficiency. More specifically, it progressively increased the sizes of two independent sets of R sets R1 and R2, where R1 is used to find a candidate solution and also to estimate the revenue of an optimization solution based on the CQB procedure. And R2 is used to estimate the budget overshoot and approximation ratio of the candidate solution. We prove that the RMA algorithm can achieve an approximation ratio of lambda minus epsilon with high probability, while causing budget overshoot of the advertisers by a factor of 1 plus rho. We have conducted extensive experiments to evaluate the performance of our algorithms. The experiments are based on 4 real datasets, including Last.fm, Flickster, DBLP, and the LiveJournal, where the Last.fm and the Flickster datasets have action logs for learning edge probabilities under the TIC model, and the DBLP and the LiveJournal use edge probabilities under the weighted castigated model. We have also set the budget and the CPE values according to the work of Asley et al. In VRDB 2017. In the experiments, we have used the 3 seed incentive models, including the linear, quasi-linear, and the superlinear cost models. All of them have a parameter alpha to reflect how the inference spread of any node U can affect its cost. We compare our RMA algorithm with 2 baseline algorithms, including TICSRM and the TICARM, with the implicit parameters shown here. In consideration of the budget overshoot, the input parameters to RMA are always smaller than those to the baseline algorithms. First, we compare the implemented algorithms on the different cost models using the Last.fm and the Flickster datasets. The results reveal that our RMA algorithm consistently outperforms the baseline algorithms on revenue under all 3 cost models, and also achieve lower seeding costs in general. In Figure 3, we study the impact of alpha on the number of seeds selected by the implemented algorithms under the linear cost model. It can be seen that the seed set size decreases when alpha increases, because the node costs generally increase with alpha, and hence fewer nodes can be selected on the given budgets. Besides, the results in Table 3 also show that RMA runs faster than TICARM and the TICSIM when the value of alpha varies. In Figure 4, we compare the revenue and the memory consumption of the implemented algorithms on Flickster and Last.fm by varying the value of epsilon. It can be seen that the revenue of RMA consistently outperforms the baseline algorithms again, and it also causes less memory usage. More detailed explanations on these experimental results can be found in our paper. We have also tested the scalability of the implemented algorithms using the DBLP and the LiveJournal datasets. It can be seen from Figure 5 that RMA runs faster than TICSIM on DBLP and achieve approximately the same revenue. However, on LiveJournal, although RMA runs faster than TICSIM and the TICAIM, it sometimes can achieve smaller revenue, which is due to the reason that the budgets used by RMA are smaller than those for TICSIM and TICAIM. However, our experimental results also show that RMA performs significantly better than TICSIM and the TICAIM on the rate of return, which implies that RMA is more profitable than these two algorithms in practice. The contributions of our paper can be concluded as follows. We have designed effective and efficient algorithms for revenue maximization in social advertising. Compared to the previous studies, our algorithms can achieve significantly better approximation ratios that are independent of the input network instance. Moreover, extensive experimental results show that our algorithms significantly outperform the compared algorithms in terms of both revenue and time efficiency under the TIC model. That's all, and thank you for listening.